This is Penghui from Zhongguancun Lab. I'll present our work Holistic Concolic Execution for Dynamic Web Applications while Symbolic Interpreter Analysis. This is a joint work with the Chinese University of Hong Kong and Zhejiang University. Symbolic execution is a foundational program analysis technique that enables many security applications, including vulnerability detection and exploit generation. In symbolic execution, we will try to treat the input as symbolic and then simulate execution over different program paths. For example, given the function f shown on the left-hand side, we must simulate the execution into such an execution tree. Let's assume the input data of this function is lambda, and in conditional statements, the symbolic execution engine would fork the execution into different program paths, and the corresponding path constraint is also collected. Ultimately, the symbolic execution engine may just pick one particular program path and accumulate the path conditions and invoke the constraint solver to give a concrete value for the specific path. For example, here, when the lambda is equal to 6, the execution may follow this particular path. However, symbolic execution is particularly challenging for web applications. A fundamental issue is the multilingual nature of web applications. Let's use PHP-based web application as an example here. So the execution of web applications typically involves components in different programming languages. For example, the web application code itself is written in PHP while all the basic PHP functionalities are realized in C. The symbolic execution engine has to reason both the web application code and also the basic PHP functionalities. Without reasoning any of these components, the symbolic execution engine would produce incorrect analysis results. To solve this issue, prior solutions takes a modeling-based approach. The key idea is that they try to convert the components in different programming languages into a common representation, such as estimate formulas, tag formulas, or function summaries. And then they often choose a high-level representation that is close to web application code and transform the low-level PHP functionalities into the high-level representation. For example, they will try to convert the basic PHP operators and built-in functions into the common representation. This is often a manual process in most prior solutions. Such a solution introduces several critical problems. First, as a manual analysis, it can hardly be complete and accurate, especially given the complexity and large number of PHP operators and built-in functions. In particular, the PHP includes over 100 PHP operators and over 5,000 PHP built-in functions. And each operator or built-in function is quite complex. For example, a basic equal operator supports the comparison between 16 operand types. On the other hand, such a manual analysis requires a large number of engineering effort. In particular, the state-of-the-art tool AnimateDat was developed using 13 person-months. That is hardly to be scalable, especially given the updates in different versions of the language. To solve these problems, we propose our new approach. The key insight is that the multilingual issue actually comes from the language interpreter, as the execution involves both parts, including web application part, but also the language interpreter part. In return, our solution wants to leverage the language interpreter to solve the multilingual issue in return. So given the very simple PHP web application code here, we can collect the web application level traces that denote how the PHP code is getting executed. On the other side, when we try to take a closer view of the PHP interpreter, we can also observe some interpreter level traces. For example, for very simple assignments, it involves the basic value fetch or value assign and value store. Each of such operations can correspond to certain PHP implementations within the PHP interpreter. we find that the PHP interpreter implements all the PHP functionalities. So given such an insight, our solution, known as Symbolic Interpreter Analysis, or SIA in short, the key idea is try to train the low-level interpreter implementations and concolically analyze them. Because every high-level PHP operation is correspondingly handled by the PHP interpreter, we can ensure we can holistically and accurately analyze the corresponding code to ensure the analysis is holistic. At the same time, the PHP interpreter itself is written in a single static compiled language such as C, thus we can directly leverage the existing mature analysis engines such as CLI or H2E to analyze the interpreter implementations. This shows to be effort saving. So given such an example shown here, we can correspondingly by hooking the PHP interpreter to get the corresponding low-level implementations, for example by expanding the built-in function implementations and collect the corresponding low-level constraints. These constraints can be fed to the constraint solvers to give a solution showing how the high-level PHP constraint can be satisfied. However, we encounter several technical challenges. For example, the underlying sim execution itself is designed to analyze the interpreter code. In other words, it is unaware of what web application code is getting executed. For example, given the code shown here, the two identical lines of code actually execute to the same PHP interpreter code because they are just identical at the PHP code level. So the underlying sim execution engine is unaware to distinguish these two lines of code during the analysis. At the same time, the system execution is designed to efficiently explore the interpreter code, but high interpreter code coverage does not indicate high application code coverage. This denotes the inefficient exploration problem in web applications. We solve these challenges with new solutions. So we find that the sim execution engines often leverage the PC value or program counters to guide the exploration. And basically, the PHP interpreter program counter is not very helpful for the web application exploration. So we define a web PC value that denotes the web application state and expose some web PC values to the underlying sim execution engine. We define the web PC value for particular instruction is as the following. It composes of the line number of the instruction together with the type of different instructions. Given the web PC value, the underlying sim execution engine will try to schedule the search algorithm according to the web PC value instead of the interpreter PC value. So given as shown in the figure, originally by searching according to the web interpreter PC value, the program would class the program states as the left-hand side. By using additional YPC states, we can better schedule the different program states for the sim execution engine. To mitigate path explosion problem, we propose several solutions. First is that we design our approach as a concolic execution engine driven by concrete inputs, so that the sim execution engine only needs to explore the closer or relevant paths close to the concrete traces. At the same time, to get rid of or avoid the HTTP server from being involved into the analysis scope, we invoke web application via a common gateway interface through environment variables, so that we do not need to invoke the HTTP server for the sim execution or the execution of the web application, but instead directly invoke the web application through the CGI. Another very important component in web application execution is the database operations. and the database operations are not embedded or included within the PHP interpreter, and it is supported by orthogonal systems such as MySQL. So to reduce the complexity when the data are passed to the database, we perform selective concretization on database data, especially when such data, symbolic data, are passed to the database systems. We try to concretize such data to reduce the complexity of the analysis. We implement our system into a tool known as SymPHP. It's a system that could enable fast symbolic execution engine prototyping. In particular, we implemented the core part at the underlying symbolic execution engine using 1,500 lines of code. This includes the basic state scheduling algorithms and the plugins to analyze the web PC values. At the same time, we provide support for PHP, especially using around 500 lines of code and 2-person weeks to expose the web PC values from the PHP interpreter or web application to the underlying symbolic execution engine. So the underlying symbolic execution can analyze the exposed web PC values and perform the basic program searches. In comparison, the SOTA solution used around 20,000 lines of code and over 13-person months to support 2 versions of PHP. In the evaluation, we include a comprehensive dataset with 7 million lines of code in total. And during our analysis, we first evaluated the syntax support. Especially, we did not observe any syntax errors during the analysis, especially including the basic evaluation and further unit testing. This demonstrates very holistic or comprehensive syntax support for our solution. In comparison, this significantly outperforms existing engines including Xing or AnimalDat with significant better syntax support. We further evaluate our system in other aspects. In particular, we evaluated the code coverage achieved by our system. We found our system could cover around 51% of application code, which outperformed the prior engines by 10% to 30%. Additionally, we apply our system to find vulnerabilities, which in turn found around 18 vulnerabilities, including 10 critical new vulnerabilities. This also outperformed AnimalDat by 20%, which used significant engineering effort. We further show several important security applications of SymPHP. In particular, how SymPHP can help validate static analysis results, how it can complement fuzz testing, and how it can be used to validate or check the correctness of other symbolic execution engines. So first, we all know static analysis could have false positives, especially static analysis identify vulnerabilities by code patterns or heuristics. It does not reason about the program paths, whether the conditions can be satisfied in practice. So we apply our system to validate the results, and in particular, we found SymPHP could reduce the false positive rate from 40% to 20% at top of our prior static analysis tool. On the other side, we show SymPHP can be used to complement fuzz testing into a hybrid fuzzing framework. So we integrate SymPHP with the SOTA fuzzing approach feature into a hybrid fuzzing approach. We leverage the fuzzer to handle the most easy paths with a very high throughput. At the same time, when the fuzzer gets stuck at some hard paths, we leverage SymPHP to solve them. This results in our on-demand concolic execution or hybrid fuzzing. In the result, we show that SymPHP could improve the fuzzing coverage by up to 85%. On the other side, since SymPHP analyzes the source code of the interpreter, it can be regarded as a gold standard for checking the engine correctness. For example, SymPHP has a very comprehensive language syntax support, so we can use it to validate correctness, especially the language syntax support of other symbolic execution engines. We deploy a very simple differential testing framework that will try to compare the analysis result between SymPHP and other symbolic execution engines. We validate whether these two engines would produce consistent results. If there is any inconsistency regarding the analysis results, we likely think there is a bug in the other symbolic execution engine. We found SymPHP helped find 10 bugs in prior symbolic execution engines. In summary, we propose a new methodology for symbolic execution of interpreted languages, a solution known as SIR, Symbolic Interpreter Analysis. SIR tackles the multilingual issue and addresses the limitations of language syntax support and engineering efforts, and is a system enabling fast symbolic execution engine prototyping. It can quickly be implemented to support the symbolic execution for different languages such as PHP, Python, and Lua, and our source code is available on GitHub. We demonstrate SymPHP has a wide range of security applications, including static analysis result validation, hybrid fuzzing, and correctness checking of symbolic execution engines. Thank you.